A planet where the sky never sees a sunrise, only fire. A world whose surface may be made of diamond, yet those diamonds are melting in a cosmic inferno. Its name, 55 Cancri A. About 41 light-years away, in the constellation Cancer, lies a planet that has fueled debate among astronomers for more than a decade. Some call it the Diamond Planet. Others argue it is nothing more than a colossal ocean of lava. And some believe it stands as proof that the universe is always more extreme than anything we can imagine. The 55 Cancri system is not a solitary star. It is a binary system, with the primary star, 55 Cancri A, being a yellow dwarf slightly smaller than our Sun, but older, estimated at around 8 to 10 billion years in age. The system hosts at least 5 confirmed planets, yet among them, 55 Cancri E is the most extraordinary. The planet was first detected in 2004 using the radial velocity method. By observing the subtle wobble of the parent star caused by gravitational tugging, astronomers knew something massive and very close was pulling on it. Then in 2011, the transit method confirmed its true size, a radius nearly twice that of Earth. Its mass is about 8 times Earth's. It belongs to a class known as a super-Earth. But super here does not mean better. It means more extreme. 55 Cancri E orbits its star at a distance of only about 0.015 astronomical units, roughly 25 times closer than Mercury is to the Sun. If placed in our solar system, it would sit deep inside Mercury's orbit, nearly skimming the Sun's surface. A year on 55 Cancri E lasts only about 17.7 Earth hours. From the beginning of one new year to the next takes less than a single Earth day. The planet is tidally locked. One side permanently faces its star, while the other remains in eternal darkness. On the star-facing side, temperatures are estimated to reach between 2,400 and 2,700 degrees Celsius. Hot enough to melt iron. Hot enough to vaporize rock. Hot enough to transform the surface into a glowing ocean of magma. Observations from NASA's Spitzer Space Telescope revealed that the planet emits enormous amounts of infrared radiation. At times, scientists detected unusual fluctuations in surface temperature, possibly caused by intense volcanic activity or shifting lava flows. They have never directly seen the lava, but every sign points to a world in constant molten motion. Then in 2012, a stunning hypothesis emerged. A research team proposed that 55 Cancri E might contain an exceptionally high carbon content. Under immense internal pressures, carbon could crystallize into diamond. If the planet's interior were richer in carbon than oxygen, it might possess a thick mantle of diamond and graphite. The idea exploded across global media. The Diamond Planet, a phrase powerful enough to ignite headlines everywhere. Some even calculated that if its mass were converted into diamond value, it would surpass all the wealth of Earth combined. But such value is meaningless because nothing could survive there. Subsequent studies cooled the frenzy. Reanalysis of the host star's composition suggested the carbon-to-oxygen ratio might not be as high as initially believed. Some scientists argue the planet may be more silicate-rich, similar to Earth, rather than composed largely of carbon. Yet the possibility of diamond existing under extreme pressures has not been completely ruled out. The debate continues. One thing is certain: 55 Cancri E is unlike any planet in our solar system. Its atmosphere remains a mystery. Observations from the Hubble Space Telescope in 2016 hinted at the presence of hydrogen and helium, possibly mixed with lighter compounds such as hydrogen cyanide. If an atmosphere exists, it is unlikely to be thick or stable like Earth's. At such proximity to its star, stellar winds and ultraviolet radiation constantly strip away any gaseous layer. Some models suggest the planet may possess a thin, temporary atmosphere continuously replenished by vapor rising from the lava ocean below. In that case, its sky may consist of rock vapor and metallic gases suspended above the surface. Imagine standing on 55 Cancri E. If standing were even possible. Gravity there is nearly twice that of Earth. your body would weigh double. But you would not have time to feel it, because the temperature would incinerate you instantly. The star-facing hemisphere is a permanent sea of fire. The dark side, once thought to be cooler, may still reach temperatures above 1,000 degrees Celsius due to heat redistribution. There are no water oceans, no white clouds, no blue skies, only the blinding glare of its star, pouring down upon a surface glowing red like burning coal. And if diamonds exist there, they do not sparkle like gemstones in a ring. They lie buried deep, compressed, heated, and distorted under unimaginable pressure. And 55 Cancri E has a density of about 6.7 grams per cubic centimeter, higher than Earth's. This suggests a massive core rich in heavy metals. An enormous iron core may occupy much of the planet's radius. Central pressures could be millions of times greater than Earth's atmospheric pressure. Scientists believe the planet may have formed farther from its star, in cooler regions, before gradually migrating inward through gravitational interactions with other planets. If so, 55 Cancri E was once a very different world, perhaps one that possessed more volatile materials before being stripped bare and scorched. Its existence forces planetary formation models to adapt. It is not a gas giant like Jupiter, nor is it a temperate rocky world like Earth. It sits at the boundary between rock and hell. See, yet what makes 55 Cancri E truly haunting is not just its temperature or the diamond hypothesis. It is its variability over time. Infrared data show that its brightness changes, as if its surface is constantly reshaping itself. Volcanic eruptions, shifting magma oceans, storms of metallic vapor raging across its skies. We cannot see it directly. We can only infer from faint light that has traveled 41 light years to reach us. And that light tells a story. There are worlds where material wealth is meaningless, where beauty, if it exists, melts under relentless heat, where every human concept of value becomes trivial. 55 Cancri E is not paradise. It is a reminder that the universe was not built for us, and this is only the beginning. The light from 55 Cancri A does more than tell us it is hot. It reveals that this planet is moving, like a living organism breathing lava. In 2016, when NASA's Spitzer Space Telescope observed 55 Cancri E over multiple orbital cycles, scientists noticed something strange. The planet's infrared brightness changed over time. Not minor fluctuations, but dramatic swings, far beyond what a stable rocky surface should produce. That meant only one thing: its surface is not fixed, it is evolving. A bold hypothesis emerged. 55 Cancri A may host a global ocean of lava, not scattered magma lakes like those on Earth, but a vast layer of molten rock covering most of the surface, possibly hundreds of kilometers deep. As the planet orbits its star in just 17.7 hours, the energy it absorbs and releases shifts constantly. The lava may be boiling, on surging, then recrystallizing in rapid cycles. Thermodynamic models show that at temperatures above 2,500 degrees Celsius, silicates do not merely melt, they vaporize. Rock can turn into gas, forming a temporary atmosphere rich in sodium, potassium, silicon monoxide, and other metallic compounds. The planet's sky may not hold water clouds, but rock clouds. Imagine a rainstorm, not of cold droplets, but of molten silicate falling from the sky, merging back into the lava sea below. A closed rock cycle, where evaporation and condensation occur under conditions far beyond any familiar geological standard. Yet that is not what puzzled scientists the most. Thermal maps of 55 Cancri E reveal that the temperature difference between its day side and night side is not as extreme as originally predicted. If the planet is tidally locked, either the side facing the star should be brutally hot, while the dark side should be far cooler. But observations suggest heat is redistributed surprisingly efficiently. This could only happen if a powerful heat transport mechanism exists, perhaps a thicker than expected atmosphere, or global lava flows acting like convective oceans. If the molten layer is deep and continuous, It could carry energy from the day side to the night side, reducing temperature contrast. Some researchers even propose that 55 Cancri E may be undergoing continuous supervolcanic activity. Not just a few volcanoes, but widespread surface fracturing and relentless eruptions. Internal pressure driven by tidal forces from the host star could constantly knead the core and mantle. The planet may be slightly stretched during each orbit, generating internal friction and additional heat, similar to how Jupiter's gravity makes Io the most volcanically active body in our solar system. But 55 Cancri E is far more extreme than Io. Measurements of its density and radius suggest that any solid crust, if it exists at all, must be extremely thin. Beneath it lies a dense molten mantle. At depths of just a few hundred kilometers, pressure could reach hundreds of gigapascals. Under such conditions, crystal structures of matter transform. Carbon, if present, could become ultra-hard diamond. Silicates might shift into mineral phases never seen on Earth. In laboratories, scientists use diamond anvil cells to recreate similar pressures. But on 55 Cancri E, the entire planet functions as a colossal compression chamber. There is another possibility that makes the story even more violent. The planet may be losing mass. At such extreme proximity to its star, ultraviolet and X-ray radiation relentlessly bombard any atmosphere. If a hydrogen-rich layer exists, it may gradually be blown away into space. Some spectral observations hint at a thin atmosphere containing hydrogen cyanide, a molecule toxic to Earth biology, yet chemically intriguing in prebiotic contexts. Escaping material could form a faint gaseous tail, similar to a comet, but composed of vaporized rock and metal, a planet evaporating piece by piece, layer by layer, atom by atom. There is even speculation that 55 Cancri E may once have been a gas-rich world, only to have its thick hydrogen envelope stripped away over billions of years, leaving behind a scorched rocky core. If that is true, and we are witnessing the exposed skeleton of a planet that once looked entirely different. Dynamic simulations of the 55 Cancri system show that gravitational interactions among its 5 planets may induce slight orbital eccentricities, enough to generate constant tidal heating. The planet is not only heated from above, it is cooked from within. A double furnace, the host star above, the planetary core below. Another factor makes it even more distinctive. The host star 55 Cancri A has a higher metallicity than the Sun. In astronomy, metals refer to all elements heavier than helium. High metallicity increases the likelihood of forming massive rocky planets. The system resembles a factory designed to produce dense material worlds. 55 Cancri E is the most extreme product of that factory. In recent years, the James Webb Space Telescope has opened new opportunities to analyze the spectra of hot super-Earths in greater detail. Each new dataset reshapes the picture of 55 Cancri E. At times, evidence suggests it has an atmosphere. At others, data lean toward a bare, exposed surface. Every result deepens the mystery rather than resolving it. What haunts scientists is that this planet occupies a regime we have no close analog for. Our solar system contains no hot super-Earth skimming so near its star. We lack a nearby sample to study directly. Everything must be inferred from faint light and mathematical models. And when the models shift, the story shifts with them. At one point, researchers believed the surface might be coated in dark carbon material that absorbs light efficiently, driving temperatures even higher. Later studies suggested its albedo, its reflectivity, may be unusually low, meaning the planet devours much of the energy from its star. A dark red world, blazing and absorbing starlight like a massive ember suspended in space. If you could observe it up close, the host star would dominate the sky, appearing far larger and brighter than the Sun from Earth. The light would not be gentle. It would blaze white and harsh, pouring onto the lava seas and making the surface shimmer like molten metal. There would be no cool breeze, no silence. If a thin atmosphere exists, it would likely be heavily ionized, generating electrical currents and plasma in the surrounding space. Any magnetic field would be under tremendous pressure. 55 Cancri E is not a flawless diamond drifting peacefully through the cosmos. It is a diamond thrown into a steel furnace. compressed, heated, distorted to the absolute limits of planetary physics. And the most unsettling truth, it is not rare. Hot super-Earths orbiting close to their stars appear throughout the galaxy. 55 Cancri A is just one among thousands. That means the universe is filled with diamond infernos, lava oceans, worlds where rock evaporates like boiling water. These places are not exceptions. They are a common chapter in planetary evolution. We are witnessing an extreme stage of planetary life, one that Earth has never experienced, or perhaps passed through billions of years ago. 55 Cancri E is a natural laboratory of ultimate conditions. Every photon reaching us carries data about matter under crushing pressure, about how planets respond when pressed against a stellar furnace. And as we continue to observe, the story does not grow simpler, it grows more intense. Because behind the lava and diamonds may lie something greater, a warning about the distant future of rocky worlds like Earth when their host stars age and brighten. But that is another vision entirely. Imagine a day, billions of years from now, when our sun expands, brighter, hotter, and Earth is pushed into an orbit similar to where 55 Cancri E circles today. No oceans, no gentle atmosphere, only a crust of rock heated until it glows red. 55 Cancri A is not just a distant exotic planet. It is a window into the extreme future of rocky worlds. It shows what happens when a planet is pushed to the very edge of physical possibility. When scientists study hot super-Earths like 55 Cancri E, they are not driven by curiosity alone. They are trying to understand a stage of planetary evolution we have never directly observed before. In the Milky Way, hot super-Earths appear to be more common than Earth-like planets in temperate orbits. That means a scenario like 55 Cancri E may be the rule, not the exception. And that rule is ruthless. If you could send a probe to 55 Cancri E, it would not stand a chance. Radiation from the host star at such close range would damage electronics in a short time. Extreme heat would soften metals and destabilize molecular structures. There would be no safe landing, no stable solid surface to anchor to for long. Even the idea of mining diamonds is pure fantasy. If diamonds exist deep inside, they are compressed under pressures and temperatures that render current technology meaningless. To reach them, you would have to drill through a global lava ocean and a superheated mantle hundreds of kilometers thick, a task far beyond the capability of any civilization we know. But what truly makes 55 Cancri important is not material value. It is the physical limits it represents. In planetary formation theory, there is a boundary known as the frost line, the distance from a star where temperatures are low enough for water and volatile compounds to condense into ice. Massive rocky planets like 55 Cancri E may have formed beyond this frost line before migrating inward. If so, the planet may once have carried significant volatile materials, including water, carbon dioxide, and methane. As it drifted closer to its star, everything changed. Lighter compounds evaporated. Radiation stripped away the atmosphere. What remained was a dense, hot, heavy core. 55 Cancri E may be the scorched remnant of a world that once looked entirely different. Planetary migration is not a vague theory. In many star systems, we observe giant planets extremely close to their stars, positions where they could not have formed directly. This suggests orbital restructuring is common. The 55 Cancri system, with its 5 planets, is a vivid example of gravitational chaos unfolding over billions of years. 55 Cancri E may have lived many lives before becoming a diamond inferno. Evolutionary models suggest that if the planet once had a thicker, cooler crust, tidal heating and continuous radiation could have melted it repeatedly. The surface may have solidified and melted again, over and over, for millions of years. A relentless cycle of destruction and renewal. Within that cycle, the planet's internal structure would also change. The iron core might contract as it cools, then expand as it heats. Mineral layers could undergo phase transitions under immense pressure, creating forms of matter we are only beginning to simulate in laboratories. If 55 Cancri E pushes planetary mineral physics to its limits, at its center, pressure may exceed millions of atmospheres. Under such conditions, atomic electron structures are distorted, material properties shift, electrical conductivity, viscosity, heat transport, all behave in ways Earth never experiences. This has major implications for understanding planetary magnetic fields. If the core of 55 Cancri E is molten and vigorously convecting, it could generate an extremely powerful magnetic field. But that magnetic field must confront intense stellar wind at close range. The interaction between magnetic fields and stellar plasma could produce massive electromagnetic phenomena around the planet. A world wrapped in radiation and electric currents, where even the surrounding space is violently stirred. On a broader scale, her 55 Cancri E forces us to rethink what we mean by a rocky planet. Not all rocky planets resemble Earth. Some are molten hellscapes. Some are tidally locked, with one hemisphere ablaze and the other shrouded in darkness. Some may lose their atmospheres entirely within a few 100 million years. That diversity changes how we search for life. When observing distant systems, we must distinguish between temperate super-Earths and hot super-Earths like 55 Cancri E. A slight difference in orbital distance can transform a potentially habitable world into a stone furnace. There is another reason 55 Cancri E has become such a powerful symbol. It is relatively close compared to many exoplanets. Just 41 light-years away, a short distance on a galactic scale. That makes it a priority target for next-generation telescopes. Every time technology advances, this planet rises to the top of observation lists. In the coming decades, space and ground-based telescopes with massive mirrors will analyze spectra with greater precision and sensitivity. We may clearly determine whether characteristic molecules exist, whether rock clouds truly form, whether its surface variations follow stable cycles or chaotic upheavals. And every answer will open new questions. Perhaps one day we will discover that 55 Cancri E is not a silent inferno. Perhaps it undergoes periodic global eruptions. Perhaps its surface restructures within just a few Earth years. Perhaps it is gradually losing mass and will alter its orbital architecture over billions of years. Or perhaps it is more stable than we imagine. A steady furnace burning longer than Earth has existed. In every scenario, I-55 Cancri E reminds us that the universe was not built to fit human expectations. Diamond, a symbol of permanence and value, becomes here a material crushed and melted. Hell needs no mythology. It exists as pure physics. And as we look up at the night sky, light from the 55 Cancri system is still traveling silently through space. The photons that left that planet 41 years ago are only now reaching our telescopes. They tell the story of a world burning, transforming, challenging outdated models. We have never set foot there. We may never will. Yet simply knowing it exists has changed how we see the universe. If a diamond planet can become an ocean of lava simply because of orbital distance, how many other worlds out there are experiencing the same fate? How many jewels of the galaxy are being melted in silence? Leave your thoughts in the comments. Do you believe 55 Cancri E truly has a massive diamond core? Or is it just a rocky super-Earth exaggerated by media hype? And if we could send a robotic mission there, what would you want to explore first?